Hello everybody, my name is Ji, come from University of Sheffield. My supervisor is Professor Ziqiang Zhu. My topic is consequent pole permanent magnet machines, and the abbreviate is CPPM machine. Here is the content. Firstly, let's start with the introduction. As shown in the left side, it is a conventional surface-mounted permanent magnet machine. We will call it SPM. By replacing the alternate PM pole into ion pole, we can achieve the structure as shown in the right side. This is the consequent pole permanent magnet machine. Shown in the black dashed line, in this flux circuit, the magnet potential is halved. But what's more, the flux resistance is also almost halved. That means the PM-caused flux linkage is almost the same. Consequently, by this way, we can maintain the almost the same output torque and reducing half amount of PM. So it can achieve cost reduction, including both fabrication and maintenance. What's more, due to the lower flux resistance, it can achieve higher inductance, so it can also realize better flux weakening performance. What's more, it can achieve lower eddy current loss and reluctance to torque, so it has been widely used in many types of machines, and also have many applications. However, it also has many problems. First of all, due to the large inductance, the large armature reaction will cause drop of overload capability. Secondly, due to the unipolar PM in the rotor, it will lead to the unipolar axial flux leakage. Due to the unbalance between ion pole and PM pole, the even-order harmonics will exist in back EMF and cause serious third-order torque ripple. And the CPPM machine tend to have lower output torque than that of SPM. In 1994, this structure has been discussed in a book, but until last 10 years, this structure has been widely investigated and many characters have been found. The next part is my work. Firstly, I built all of these kinds of consequent pole machine structure. In the second one, the CP half model, the PM amount is half of the SPM counterpart. And in the last three models, they all have the same amount of PM and SPM machine. Here are the results. From the first figure in the orange line, we can find that the CPPM machine can improve the magnet utilization, especially under light load condition. But it is also obvious that the overload capability of CPPM machine are worse than that of SPM machine. In the second figure, the yellow line, Harbach CPPM area can improve the output torque. And in the third figure, it is obvious that the reluctance torque is more obvious when the current density is large. This will be explained by the next slides. As shown in this formula, the reluctance torque is mainly determined by the difference between LD and LQ. According to whether the slot pole number combination can be expressed by the formula on the right side, consequent pole machines can be divided into two groups. So here, a 12-14 and a 12-8 machine are set as an example in the following analysis. For the 12-14 machine, opposite phasor teeth can be compensated with each other. So that's why the inductance waveforms are smoother than the other machine. But for the average value of LD and LQ, we can see that for both of these two machines, the difference between LD and LQ is small. It's worth noting that in the analysis, I found that the relation of LD and LQ will change with the ion pole arc span, but the differences are still small. That means the reluctance is small, especially under light load condition. But reluctance torque is proportional to the square of the current. So, only when injected current is large, the reluctance torque is more obvious. This is the explanation of the previous slide figure. However, large input current will also induce saturation problem, which limits the reluctance torque improvement. So we can draw a conclusion that in the conventional consequent dipole machine, the reluctance torque is quite small. The next part is the elimination of even-order harmonics and unipolar end-shaft flux leakage. Due to the unipolar PMs in rotor, it will lead to unipolar end-shaft flux leakage and even-order harmonics. This will cause magnetization risks of mechanical components and torque ripple. The main idea to solve this problem is to set bipolar PMs in the rotor. So firstly, some people try to use actually bipolar magnet as shown in the 3 papers. However, it is obvious that the structures are quite complex. And for other papers, researchers try to use circumferential bipolar magnets as shown in these figures. What's more, the tangentially magnetized PM are set here to improve the output torque. So similarly, I try to propose some structures to eliminate even-order harmonics in EMMF and unipolar end-shaft flux leakage for some other slot pole number combination machines. As shown in this figure, in the second column, I call it MCPM1. We can see that the rotor are divided into 8 parts, and the tangentially magnetized PM are set here to improve the output torque. By removing the unnecessary flux barrier in rotor, we can get the MCPM2 as shown in the third column. What's more, by introducing the flux gap at the end part of each PM, I can get the MCPM3. The reason why for this kind of machine can eliminate the even-order harmonics can be explained by these 2 figures. From this figure, we can see that for MCPM machines, 2 teeth belonging to the same phase are facing to the opposite position of rotor in mechanical structure with same electrical phasor. So the even-order harmonics in back EMF of one coil per phase is antiphase to the even-order ones in other coil. Here are the results. We can see that for the 3 MCPM machine, the torque ripple are much smaller than that of conventional one. And for MCPM3, the average torque is almost the same as conventional CPM. Also, the proposed 3 machines have lower core loss. This can be explained by the lower saturation level in both stator and rotor cores. What's more, for MCPM3, although the PM utilization ratio is lower than that of conventional consequent dipole machine, but it is still much larger than that of SPM machine. However, for MCPM3, there are also some shortcomings. The larger number of magnets, which is even more than that of SPM counterparts, will also lead to higher manufacturing cost. Okay, that's all. Thank you.